Hello, in this video I'm going to show you how to disassemble the game that is running on the Commodore 64 that you can see on your screen right now using the Merlin 64 macro assembler development software package, which came out in about 1985. We'll then look at the code together and analyze and see if we can learn how it works, and then hopefully make some changes to it and build our own custom version of the game. The Merlin 64 assembler did not need any special hardware to disassemble software. All you needed is a Commodore 64, a disk drive, and a whole bunch of patience. The game is called Astro Panic. This game was written entirely in assembly language and is an early type-in game from the 1984 Computes Gazette magazine. You needed to type in a program called MLX in order to even type in Astro Panic. MLX is a program that lets you type in binary values straight into memory and then save it. The listing for Astro Panic, it's about 2 full pages of binary data. It took me about 2 hours to type it all in. As you can see, Astro Panic is a game where you need to defend your cannon by shooting waves of alien saucers. Each wave has 7 saucers. The game has some simple sound effects when you shoot and destroy the saucers as well. From just looking at this gameplay footage, you can see that the game appears to use all 8 sprites. There seems to be a raster interrupt routine in place as well, because you can see that the border color has 2 colors, the top part being black, the bottom part being gray. I'm guessing the laser front from the cannon is a custom character, but we'll see when we get into the source code. For this project, we just need 3 things: a binary of the Astro Panic game, a copy of the Merlin 64 macro assembler software, and a copy of Mapping the C64, which is just an essential book for doing any kind of disassembly. If you wish to follow along with the video, all of these materials are available on the GitHub link provided in the description below. Alright, let's get started. Before we start the disassembly process, we want to take a few moments to review the labels table. On the Merlin assembler disk, you will see a file called labels.o and a program called labeler. Labels.o is an internal memory table that contains names assigned to commonly used memory addresses, such as FFD2 assigned to the name CHROUT. You can edit this table by using the labeler program. As you saw, the labeler program just loaded into memory the file labels.o, and here you're given a chance to list what's in a table. These are the most commonly called kernel routines, and you can see names assigned to some of the more commonly used page 2 and page 3 memory addresses. All right. At this point, you're given the opportunity to add labels, maybe delete ones that you don't necessarily want to use in your code. Then you just press Q. Here you're given a chance to save a new copy or hit run stop to not. We're going to press run stop because we don't want to. And that's it for the labeler program. So now we're going to load up Merlin. Merlin has an integrated assembler, editor, and monitor. What Merlin doesn't have integrated is the disassembler. That's a separate program. And to get to that program, we're going to type G, run program. We type in source, R-O-R, Sourceror, cute. So the first thing it does is it loads that labels table that we just looked at a few moments ago, and now it asks us to load an object file. Sourceror does not work with 2 disk drives, so we're going to have to take out our Merlin disk and put our Astro disk into drive 8. So we're going to say yes for this, and we're going to type in Astro, and it's going to load Astro into memory. Now you notice the phrasing it uses. Original location is C000 to C65A. That's because it actually loads the program into the actual memory addresses of 0800 until however long the program is. And then from that point up until close to C000 is actually where the source code is generated in RAM. Sourceror itself sits around C000 until the end of memory, and it stores a lot of its data underneath the kernel ROM. So we're going to press a key to get the process started. So the way assembly language programs are generally written is there's a mix of code and a mix of data together. So we're going to start from C00 to disassemble the code, and we're going to be looking for pockets of data while we're doing it. When we see data, we're going to use the H command, and that's going to, instead of taking code out, give us like data statements. So let's just start taking some notes real quick, and again, to note our memory addresses of C000 through C65A, and we can use our Windows 11 calculator in hex mode to calculate the size of the program, and it is 1626 bytes long. So let's get started. So to get started, we type in C000, the start of a program, and the letter L. And that's going to start disassembling it. What you see on the screen, of course, is org $C00, which is the start of our program. The middle column contains the assembly language that was created through the process. The machine language portion is that left column, and you'll see that each row starts with the memory address and up to 3 bytes, because assembly language on a 6502, there's only up to 3 bytes per instruction. So you'll see the first byte is a 4C, which of course is the opcode for the jump instruction. And what you're looking at here is the Commodore 64 programmer's reference. So you can kind of see how it comes together. You'll see that opcode just needs 2 bytes for a memory address. As programmers, we read the column in the middle that says C10B, but the 6502, being a little Endian CPU, actually stores it backwards. It stores the smaller value first, the 0B, and the C1 after it. But in any case, this is the code. And that far right column is a visual display of what it might see if they are characters that it can present on the screen. To disassemble the next screen of code, you just press L and it'll continue along. Right? You'll notice if you look into your typical assembly language program, you're going to see really 3 address ranges, right? We're going to see like jumps and JSRs into code within our code range. So you'll see things like that jump C105, that's clearly within the range of the code of our program. Anything you see that goes out in addresses in at D, 000 to DFFF range is going to be the software talking to like the VIC chip, the SID chip, or other devices that are attached to the Commodore 64. Anything we see in the E00 to FFFF range is most likely calls to the kernel. And anything in that A00 to BFFF range is going to be calls to the basic ROM. So let's continue and see what we see here. Here we go. FF9F is a kernel call. So if we just want to scroll through a whole bunch of more pages, we can actually just type a bunch of L commands and they'll run consecutively. And what we see here clearly appears to be just code. Now you'll know when you see data because it'll just appear as a bunch of breaks or unrecognizable assembly language. So we're just going to kind of keep cruising here, and again we're looking for data. Well, a lot of code in this, which is good. Looks like code. Ooh, this looks like data. This is what I was talking about. So you're going to see a section of just breaks and what seems to be nonsensical code. I think the data starts at C4E2. So we're going to tell the disassembler that. We're going to say C4E2 H. H is we see data. Instead of trying to disassemble it into source code, just capture the bytes and store it as like data statements in a basic program. The next parameter you can put is how many you want to capture. It wants a hex value, which is kind of annoying. And the highest number you could put is 240, which is F0 in hex. So we're going to try to capture 240 bytes into data statements. And you'll see it's going to create hex statements with the binary code in there. Now, there's a kind of a weird thing where it doesn't always capture 240. So we'll see what we did here. We're going to type in L, press enter, and it's at C5D2. If I take C5D2 and I subtract C4E2, I do get F0, so it did capture the correct amount this time. So if I were to take the end of the program, which we know is at C65A, and subtract C5D2, which is the address on our screen, I get a hex value of 88. So let's try to dump the next 88 bytes, trying to get the rest of the memory out. So we're going to type in C5D2, hex 88, and we're going to see more disassembly. Not sure that got out everything, so we're going to type in L and see what it's up to. And you'll notice it didn't quite capture everything. I'm not quite sure why, but that's okay. We can do some more math and see what's left. So we could take C65A, and we could subtract C61A, and we still need another 40 bytes. So we're going to do C61A, hex, and I say 40. When I say 40 bytes, I'm sorry, 40 hex bytes. All right, so we're going to press enter. Grab more data, we're going to press L, and oh, perfect, we see the ending address of our program on the top of the screen. So now we type in C65A and the letter Q. This lets the disassembler know that we got everything we wanted and to start producing source code from it. Now this process takes a while because what it's doing is it's going through all of the source code that it captured, and it's looking to either create new labels for addresses that it found or references to that labels table that we brought in. And it's going to take a little while, so I'm going to let this sit for a moment. Okay, at the end of the process, it gives us a chance to save the source code. We're going to say yes. type in ASTRO. It's going to automatically add a .s to the file name, and it's going to create Merlin compatible source code that we can use to reassemble it. All right, we're done here. Let's reset the computer. All right, let's load Merlin back up. And this time we'll be using both of our disk drives. We're going to put our source code in drive 9, and we're going to leave the Merlin disk in drive 8. So let's first start by switching to device 9 by pressing the D key. Type in 9, press enter. And we'll press the C to get a catalog of our disk. There's the source code that was created by the disassembly process. And of course, there's Outtro, the original binary of the game. So we're going to use the L key, and we're going to load in Outtro, the source code. It will automatically append a .s to it when I press enter for source code. Let's take a look at the code that it generated for us. Press the P command to print the source code to the screen without line numbers. There we go. So now we can get an idea of how this disassembly process worked. Clearly we could see the org $C00, which of course is the start of our program. Here you can see that the label created by the disassembler is letter H, followed by the memory address that was in the original disassembly. Later we're going to go through the source code and renaming those labels to be something more meaningful. Right away we can see that this is a routine that installs an interrupt vector. This is going to be really fun to look at a little bit later on. And I'm going to show you the end of the project by printing lines 500 and above. And we'll kind of get down here. There we go. I'm going to pause it with the space bar. From this point on to the end of the program is just all data. This will probably take us the most time to deconstruct as we go through the program, figure out what it's pulling out of these different parts of data, and rearranging the code into something much more readable. I'll press enter to continue on a little more. Here we can see the first two labels came out of the label section, 28D being the shift flag to see the shift keys held down, and CINV, or address 0314, is the user-defined interrupt vector. After that is a short list of various memory addresses that it's reading and writing to. BD, CD is a very common routine in the basic ROM that will print a 16-bit integer to the screen. Go down a little bit here. All of these C addresses are references to our data section, which is anything from C4E2 up to the end of our program. It'll be really interesting to see what the code is pulling out of there. I'm sure it's going to be sprite data, possibly a custom character, and maybe some sound effect data. Here we could see addresses into the IO section, those D addresses. All right, we can see the border and we can see the screen color. I know those right away, DO20, DO21. If we continue on, we'll see a handful of kernel calls at the end. We get to see that it's clearly using a kernel to grab a key, to write characters to the screen, and to get input, and to move the cursor to a certain position, which is what the plot command does. So before we start diving in and renaming labels and reorganizing the code, we want to assemble this project as it is and make sure it works before we start touching anything. We'll use the ASM command to assemble it. It's going to ask me if I want to update the source. We're going to choose no. And what updating the source does is it lets you put a comment at the very top, like, last assembled on today's date or something like that. The assembly process takes a little bit. It's going to show you all the code as it's assembling. If we press F1, it'll stop printing the code to the screen, allowing it to assemble much quicker because it's not trying to drive the screen at the same time. And there we go, it finished. A great sign is that it did it with 1626 bytes. We know that's the right size of our program. So let's quit out of the editor, and now we're back at the main menu. What you'll notice different on the main menu now is that you can see that our object code is in memory from C100 to C65A, the exact addresses we were expecting. Internally, Merlin actually doesn't put your object code there. Where the object code is actually in memory is starting at address 8000. So if you press E and you want to edit, and we go to the monitor, and I were to disassemble C1000, you'll notice that that is not the code that we assembled. It's some other code, right? But if we take 8000 and list it, we can see our code. But what's interesting is you'll notice that all the code that's there is if it were at C000. So that's an important thing to know. If you're writing code in Merlin and you want to run it through the monitor, the org really has to start at 8000. But for us, we're assembling it, and we're just going to write it to disk as a program. So to do that, we're going to use the O command. And defaults to ASCII. It will add a .o to the file name automatically. So we're going to press enter. And now we've assembled the program, and now we're going to run it and make sure it works. All right. So we'll switch to drive 9. And I'll show you the disk really quick. And we're just going to load this one here in ASCII.o. And then sys49152 to start it. And there it is. So we're able to disassemble it, and we prove that the disassembly is good by reassembling it into a new file. All right. All right, let's fire up Merlin, and let's get into this project and start cleaning up the source code and making it presentable. All right, so drive 9, load our source code in. And the first we're going to do is ask the editor how much memory we have free. We have about, a little bit less than 8K of code used, and we have 22K of RAM free for our source code. It sounds like a lot of memory, but we're going to be adding probably a whole bunch of commentary and some formatting to clean up the code to make it readable. So we do want to free up some RAM, and we're going to do that by getting rid of some unnecessary labels. So if I do a search for these addresses in that $D000 range, we'll see that there's a whole bunch here. And all these labels from line 630 down to 666, we just don't need those. So we're going to get rid of those. Now, all those label references are still in the code, right? So if I do a search for HD, we're going to see all these references. And we're just going to change those from HD to $D. Do them all. And now we've freed up a bunch of RAM. How much RAM did we free up? Let's see. Not bad, 500 and something bytes. So that's a pretty good start. Now let's actually make some changes here. When I was looking through here before, we noticed line number 16 there has a store to 0315. We remember that CINV was an equate to 0314, and those two memory addresses contain the memory address of the interrupt handler. You can see that it's loading the high value into 315, which is CO, and a low value 24 into 314. So that's memory address CO24. The problem is we're not quite sure where that is, because if we scroll through here, we don't see an HC024 address. So let's just do a quick assemble and see if we can figure out what line of code that is on. And the reason why I'm assembling it is we're going to look into monitor, and we're going to go see what that address is, and then we can put a label to it, and then we can use that to set up the interrupt vector. All right, so we're going to go into the monitor, and we're going to disassemble from line 8000 down. And you can see that 8024 is that line that has load into accumulator address $D012. So let's remember that. It's right after the RTS. So we'll quit back to the editor. And there it is, line 19. So we're going to put a label at line 19. And we're going to go to insert mode with Control I, and we're going to type in IRQH. This is an IRQ handler. All right. And now we want to change the numbers that are used at line 15 to, instead of being, load in $CO, we want to load in the high value of IRQH. All right, and we want to edit line 13, where instead of loading 24, we're going to load in the low value of IRQH. All right. So now at this point, IRQH is a label, and more importantly is it's now relocatable. Because CO24 being hard-coded into the code, if we were ever to try to assemble this at a different memory location, it wouldn't work. But now it'll actually work correctly, because it'll insert the correct values for whatever memory address IRQH would be if we were to change the origin of the code. Let's replace that label H0315 with a direct address to 0315. So let's first edit line 16. Oops, we'll make this a $0315, and then we just got to figure out where that H0315 is. There it is at line 597, so we're going to delete 597. So let's take a look at the code again, and let's see what we want to do next. The very first thing this program does is jumps ahead to address C10B. And if we go down and we keep looking for HC10B, which is way down here, there it is. The first thing it does is it JSRs that second line of code at HC003. We know that from just looking at the code that HC003 is code that installs an interrupt handler. So we're going to rename that label. We're going to do a change, HC003 to, I don't know, INSIRQ, install interrupt. We'll do both of those. So now when we list the code, we're starting to see some structure to it. We could see that, oh, there's a install IRQ handler at line 4. The interrupt handler itself is at line 19. Let's add some spaces here just to kind of break the code apart more. So we'll insert a blank line at 4. And then we'll insert, I want to say it's going to be line 20 now that it's moved down one. Let's see if that's correct. So we'll list this. And cool, I got it right. Now that code's starting to come along, we can clearly see the code broken up. We've got our jump ahead to HC10B, which we're not quite sure what that does, but it does. The first thing that thing does is call our install interrupt handler, and then there's our interrupt handler right under it. What it does yet, we're not quite sure. So at this point, I'm going to assemble the code, save the source code, write out the object code, reboot the machine, and test it. I'm going to be doing that a lot through this process, but I'm not going to show you that process every single time because you'll just get sick of seeing it over and over and over again. So I'm just going to put a little blurb on the screen that that's what I'm doing. Let's label this HC10B address as start, because that is where the program starts and where the initialization code is going to be for the game. I'm going to do a change, HC10B, and we'll call that label start. All right, let's take a look at the code at 121 on, and let's see if we can figure out what's going on here. First thing it does is it loads a 4 to 0 page address FC. FC is a pretty safe spot. There's a few bytes in that region that assembly program languages can use without getting in the way of BASIC or the kernel. So that's probably a working variable for something, but who knows at this point. So we're going to skip that piece of code for now. This next block starting at HC114, this is copying 8 bytes of data from the beginning of our data section, right, that we identified in C4E2, and it's copying it into memory address 3800. 3800 is an unusual address. You know, our application is in that C00 to C65A area. It's not a kernel call, it's not a basic call, and it's not going to I/O. It's either putting custom character data there or sprite data there, because that address fits within the first 16K of memory, which is what the VIC chip is by default looking at. And it's towards an area of that 16K that's not really inhabited by anything. And because it's copying only 8 bytes of memory, I am pretty confident that that is a single custom character. This next block at HC122 looks like it's zeroing out 8 bytes of memory at 3900. Not sure what that's all about. Maybe it's building a custom character that's blank. Who knows? Let's see if that C4E2 does it in fact point to a custom character. So let's take a look at that memory region. So we're going to do a find on HC4E2. See what line of code that begins at. It's at 568. And let's list this down here. If we look at the first 8 bytes there, does that appear to be a custom character? Well, how can we find out? Well, custom characters are pretty easy to deal with. We can bring up Notepad, because I'm using Windows here, or Notepad++ is what I'm using. And let's put 8 bytes down here. So 30, 10, 20, 30, 10, 20, 30, 10. There's 8 bytes. If I turn each one of these into binary, and it appears to make a picture, then that's probably a custom character. So we're going to bring up our trusty Windows calculator, because this is such a great tool for converting hex to decimal to binary to octal. And we'll start with, these are hex values, we'll start with 30. 30 in binary is this, so we can plop that here, plop that here. We can take 20, and then we can plop that here, here, and then 10. Then we can plop that here, 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 and here. That could be a picture, and if we wanted to see it a little bit more clearly, we can replace our zeros with a space, and that looks kind of like a bolt. This is either like kind of a squiggly bolt character, or it's a multi-color custom character where each cell is 2 bits wide to determine the color. Either way, I'm pretty sure this is our laser bolt. But let's prove it. How do we prove that this is our laser bolt? Well, we could make a version of this program where we replace those 8 characters with, say, all bits on, to make it just like one giant block. And then if we were to assemble the game and load it, and we saw a giant block for our laser blast, then we will be sure that that's the custom character. So let's edit line 568. And let's just make these all Fs, right? So go 1, 2, 3, 4, 5, 6, 7, 8. All right, let's assemble this, and let's see if this changes the shape of our cannon's laser shot. Oh yeah, that's definitely our laser shot. Although I think I made this game a lot easier all of a sudden. Look at the size of that bullet now. Okay, so that's clearly our custom character. All right, let's jump into the editor and let's take a look at that line of code. I think it was down by 568. So knowing that that's a custom character, we want to isolate those 8 bytes by itself and give it a meaningful label, right? So let's copy that line first. We'll copy 568 to 568. So we've got a copy of it, and now we've got 2 of those. We're gonna keep the top one and make this the bullet data. So let's call this, I don't know, BLT data. Oops. Make sure we keep that. And the bullet data is these first 8 hex values. All right. Then we're going to edit 569. We're going to get rid of this HC4E2. Whoops, let's do that again since I just messed that up. Okay. HC4E2 is gone. And then this is like the opposite. We want to keep the remaining bytes. All right, so now if we look at 568 on, oops, list 568 and forward, we've got our bullet data, and now we just need to change the label that was used up here to get to it. Oh, we'll just change HC4E2 to BLT data. There should only be one of these. There it is. And now our code clearly has that custom character isolated to that one line. All right, so once again, if we search for bullet data, that range of code is at 125. And let's see what else we can do to clean this up. Let's rename this loop. Since this is loading the bullet data, I think we can change this HC114 label to, I don't know, BLT load loop. Not quite sure how readable that is, but we'll go with it. Also, that memory address 3800, because that is a direct address we're writing to, and it doesn't really need a label. It's not part of any code that needs to be relocatable. I want to replace that H3800 with just a hard reference to that address. So we're going to change it like this. We'll do all of them, and then we're going to delete line 608. Let's remove this H3900 label. Let's change this H3900 to, oops, to $3900. We'll grab both of those. We'll delete that extra label. We don't really need that anymore. And I want to change the name of this reference, HC112. And like I said, it seems to be zeroing 8 characters, so we're just going to call it 08 for lack of a better name. All right. All right, let me do a compile reload test, and then we'll look at this next section. All right, the good news is the game still assembles and runs correctly. Nothing is broken. This is a loop that's copying 256 bytes from C4EA, which is a part of our data section within our program, to memory address 3A00. I'm pretty confident that this is sprite data, and we're going to prove it by looking into that memory and seeing if we see sprite shapes after we load the program. I'll explain how we're going to do that in just a second, but let me take a really quick side diversion and explain how sprites work on a Commodore 64. The VIC chip, that's the chip that displays the video on a Commodore, can only see 16K at a time, and by default it could see the first 16K. A sprite itself is defined in a 64-byte data structure, giving us a 24 pixel by 21 pixel image. Or, if we're using multicolor mode, 12 by 21, because then each pixel takes 2 bits. This game is definitely multicolor, so that's what we're looking for, is a multicolor image. If you take 16K and divide it by 64, you get 256. This means a VIC chip can point a single hardware sprite to one of 256 sprite shapes at a time. This means that you could load like 16 shapes of memory for a sprite, and then just change the pointer to the hardware sprite to one of those in order to perform animation. But now we're getting ahead of ourselves. So if we were to take memory just 3A00 divided by 64, we get the number 232. That means our sprite should be sitting in slots 232 through 235. So let's go prove that. So what are we going to do? We're going to restart our computer. And we're going to use another typing program from Compute's Gazette called Sprite Magic. So I'm going to put that disk on my disk drive, and I'm going to copy it to our source code disk in drive 9. Jiffy Does makes it really easy to copy single files between 2 disk drives. We use $$ to load the directory into memory like a basic program. You go up to the program you want to copy. We're going to press Ctrl-W. You want to copy Sprite Magic. You say @x9, which means I'm transferring to drive 9. And then you just run the program. And that's going to copy Sprite Magic to drive 9. You can copy multiple files too just by Ctrl-Wing a bunch of different files. Alright, so let's load the game up first. 49152. At this point, it's obviously copied the sprite shapes into that 3A00 section. So let's press Run Stop Restore to exit the game. And now we're going to load Sprite Magic. Sprite Magic also sits at 49152, but we're looking for the sprite at area 3A00. So let's sys 49152. Now we're in Sprite Magic. In Sprite Magic, I can use the minus key and plus to go between the different slots of the VIC chip. And each one of these, as you clearly see on the screen, is a 64-byte image. So we should see images around 235. So let's see. Oh, there we go. It looks like a spaceship. Possibly an explosion. Our saucer. Another spaceship. I guess that's our cannon. And then garbage. So we proved it. There is sprite-shaped data there. Now, I did say that they're multicolor sprites. Sprite Magic, if you press F5, switches to multicolor mode. All right, so now that we know the shapes are there, let's get back to Merlin and let's edit our code. All right, let's load Merlin back in. So the code is copying from memory address C4EA. We don't actually have that memory address labeled in our code yet. So we need to go down and see if we can figure out where that is and label it. So if we look around, I think it's like 550, we're looking for our data. Here we go. We can see our bullet data is at 568. We could see the 8 characters of data that are there. And then clearly right under it where 569 is the start of our sprite data. Here, however, we kind of run into the limitation of a 40-column screen on a Commodore 64. The lines that contain 16 hex values go into 2 lines, making it tough to read. And when we get to the next part, we want to start annotating the right side of the code with some commentary. It's just going to be really hard to work with in 40-column mode. Luckily, Merlin gives us an 80-column option, a software 80-column option. The text is slightly harder to read, but it's definitely worth it to have 80 columns. So before we switch over, let's take a look at how much memory we're using right now. We have 22K of source code left with 7.5 used. That's pretty significant. So how do we get 80 column support? Well, we're going to quit out of here. And before I do it, you'll notice that the source code is stored from memory addresses 0800 to 26AE. To get 80 column mode, I'm going to press C so you can see it. Oops, let's change the device back to 8. Press C. There's a program called CHRGen80. That's the 80 column character generator. So you type in G, we type in CHRGen80. You'll notice that our source now is 4000 because we give up a whole chunk of memory that would normally use the source code to load the 80 column mode in. So let's go back to drive 9. Let's load in the source code again. Now you'll notice I'm still in 40 column mode, so you're probably thinking, where is it? So let's take a look at lines 560 plus. And again, this is what it looks like in 40 column mode. The way these user-defined modules work in Merlin is you type in user and it switches to the user-defined module. So now we're in this 80 column mode. Text is harder to read, but we now have 80 columns of editing power. It's great. So now we can actually see it very easily, and there's tons of room for comments. If we type in len, however, you can see that we've given up probably about 13K of space so we can have this 80 column mode. But it's okay, it's worth it. If we happen to run out of memory for source code, we can split our source code up into multiple files, and it's still not a problem. From here on forward, I'll be using the 80 column editor. Our sprite data starts on 569 and goes down to however many 256 bytes are. So we need to split this section up into 4 chunks, one for each sprite, and put some labels on it so it's very easy to read. So through the use of magic, so I'm not going to have you watch me make all those edits, that'd be pretty boring. So let's fast forward. Okay, so here you can see I have the 4 sprites broken up into chunks, so it's very easy to see the sprite definitions in each one. And each definition has 64 bytes of data. Here's the rest of it. And then I marked the end of canon 2 with other data, because there's more stuff behind that that we still have to account for, but not too much. So let's take a look at the top part of the code, which I think was around here, where it actually loads the data in. And I went in and I added some commentary to it. So in our 80 column screen, I can now add in, some play-by-play stuff on the right side. So there's our loop for 08. Right under it is where I re-annotated it for loading the sprite data in. So it loads 4 sprites in. And if you go down a little bit more, this section is setting the sprite pointers to slots 232 for the canon and 233 for all of the sourcers. For all sprites, because a lot of the sprites are controlled by registers where there's 1 byte, where toggling each bit turns on and off a thing. So when we load an FF, it's all bit set. And then what we're saying is all sprites will have multicolor on. We'll use the normal width, the normal height. It sets the bit 9 for the X position of it to 0. Because when sprites move to the right side of the screen, it goes from 255 to 256, and you need a 9th bit. That's what DO10 holds. And then it sets some colors. It sets the shared multicolor 0 to cyan. It sets the shared multicolor number 1 to purple. The Y position of the canon is set right here. I figured that right after the saucer data, it loads in 8 different colors for each of the different saucers. So at this point, we seem to have covered how the game sets the sprites up, loads them into memory, and assigns color, and gets ready to display them. I'm going to end this video here and continue to another video, because I think the next spot we're going to be looking at is the raster interrupt routine and how it actually performs the animation of the game, and we get some of the game logic. So that should be really, really interesting. Even at this point, you can pull down a source code yourself from GitHub and put your own sprites in it, and you can start playing around with it. Well, I hope everyone found this video interesting and maybe even a little bit educational. And I look forward to getting the next video out to you guys, hopefully in about a week or so. Thanks for watching. Take care.